Hello, welcome to this tutorial, which is, I suppose, about how floating point numbers work inside the computer. We are going to explain what the terms mantissa, exponent and sign bit mean in terms of the Institute of Electronics and Electrical Engineers single precision, that is 32-bit standard. Now 32 bits is also known as 4 bytes, that is 4 times 8, and computer memory can store quite a wide variety dynamically of floating point numbers. They're actually binary floating point numbers, so instead of a decimal point, it has a bicimal point. That is, on the left hand side of a binary number that is a decimal number in the sense of being a fractional number in decimal, when it's converted to binary, it has a binary integer value on the left hand side of the bicimal point and a fractional binary number on the right hand side of the bicimal point, and that point is said to float. Now, in order to make it float, what we do is actually change its value, so it can float, as it were, from the left or the right of a number. Take the number 12.34 for example in decimal. This is really 12 with 3/10 added on and 4/100. That is, the part here is 3/10, which is obviously 0.3, but it's also 3 divided by 10, or 3 divided by 10 to the power of 1. And this is 4 divided by 10 to the power of 2. So it's 3/10 plus 4/100. But we read it as 12.34. If we were to really expand this, we'd say that that really is times an exponent of 10. So that is 10 raised to the 0. Like this, because 10 to the 0 is really just times 1. If we make this minus 1, in order to get the same value out of here, we have to say that this has moved the decimal point in which direction? Well, we'd have to move it to the right, to here, to make the same value as 12.34, because we would, by multiplying by 10 to the minus 1, say that we're actually multiplying 10th. That is, we'll be moving it 1 back. If I put here minus 2, we've changed the number by really a factor of 100. So now it's 1234 times 10 to the minus 2. Now the thing is, we have something called normalized numbers. This is scientific notation, and when it's normalized, what we're saying is it's got to have a value for this part, and this is the mantissa. This part has to have a value that is between 1 and 9, or in other words less than 10. And so we can't have 12.34 as we started out, we could have 1.234. But that is moving the decimal point 1, 2, 3 back. So if we move the decimal point back 3 times, we have to add the indices here. So this is actually plus 3, which gives us actually 1 and that is of course 10 to the 1 is 10, so we're just multiplying 1.234 by 10 to give us 12.34, which is what we started out with. Now, by allowing the decimal point to float right or left, we're able to get very large numbers, very different values dynamically. The reason for this is because in this short space, which we're just using 4 digits here, we're able to change the power that we're raising it to, the exponent. So if we wanted to actually have a very small number, we could have an exponent, disregarding what we started with now, of say minus 34, and that's a very tiny number. Or we could say an exponent of 23, which is a very large number. So by simply changing the exponent, we can change the value of the number we want to represent. It's literally powerful. We can do the same thing if it's all binary. So if I take away this 10 by literally deleting it and say no, it's 2 raised to the power. If we have 2 raised to the power of 2, that's 4. But if we have a number here that is a binary number, we can't have anything other than 1 or 0 in binary, as you know. So not 9, 0, 0 and perhaps a 1 there. This number is in fact a binary number, and the Bicimal point is here. It has an exponent of 2 and a mantissa of 1101. The sign, if we had a sign bit, would be positive, because this is a positive number. There's no negative sign anywhere about. And if we get ourselves a calculator, like the Windows calculator here, we can actually put this into the calculator. Well, the calculator does not like fractional numbers, this one, but we're just going to say what this actually means. So if we put it into binary, we find that 1101 in decimal is in fact 13. Does that help us? And the answer is sadly no, because it's actually a 0.1101. But actually it could help us. What this is 1/2 plus 1/4 plus 1/16. Now that is actually also able to be worked out like this. The calculation we had before, which was 13, that's those numbers in denary, divided by 16, which is the power of this place here. And when we do that, we get 0.8125. So this is 0.8125 in decimal, and it's going to be multiplied by 4. Or rather, I should have said, my apologies, that it's the 0.8125 added to 1, so that's 1.8125 times 4 gives us 7.25. Now if you look at 7.25, you can actually see that in this pattern. If we just say, well look, let's have the point there, let's float the point from there up to here. Well, when we do that, we have 7 plus no halves but 1/4, so 7.25 here. But of course, if we've moved the Bicimal point 2 to the right, we have to change this, say -2, and what we actually get is 0, and 2 to the 0 is 1, so that is in fact 7.25. We could play around with this for a long time, but what we're trying to see is that the mantissa is this part here, but it's normalized so it's always 1. That is, it's less than the number of the base. In decimal it's less than 10. Well, it's less than 2, and so it's got to be a 1 or a 0 to be less than 2. So we always normalize really to 1. So this is scientific notation, and this is the mantissa normalized 1101, and this is the exponent 2 in this case, and the sign is of course positive. Notice that there is a times here, and that's implicit, or it's explicit here, but it's implicit in what we're going to be looking at next. Let's look at the number minus 1.5 base 10. Minus 1.5 times 10 to the 0 is equal to minus 1.1 binary times 2 to the 0, because the 0.1, the Bicimal point here, and the 1 here signifies 1 over 2, that is a half. So there are 4 parts to a scientific number: the sign, the mantissa, the times, and the exponent. In this example here, we show by colour. The sign here is shown in yellow, and the mantissa shown in red, and the times shown in purple, and the power shown in cyan. And we can map the components to their colours. So we have this pattern in 32 bits. We have the sign bit, which is 1 bit, the exponent width, which is 8 bits, and the mantissa precision, which is 24 bits. We can add the bit counts here. In actual fact, this is bit number 31, and these bit numbers can also be identified. That the sign bit is bit 31, and the exponent width, the 8 bits, is really bit number 30, not 20, beg your pardon, 30 through 23. And the mantissa bits are therefore, perhaps you can work these out, (24) through 1. Just joking. Obviously it's 22. This is next to 23, and it doesn't go to 1, it goes to 0. If you caught that. Okay, we'll see another representation of that bit later. So we must remember that the mantissa is always going to be normalized. That is, it's going to have a value which is fractional, but it's going to assume that its whole number part is 1. So it's going to be 1 point something. So let's do an example. We're going to look at minus 0.75 in decimal. We need to multiply it by 2 because it's less than 1, and we need to get at least 1 point something or other. And in Bicimal, the Bicimal point or decimal point doesn't matter, it's still going to be 1 point something. So we can say that minus 0.75 times 2 to the power of 0 is equal to minus 1.5 multiplied by 2 times 2 to the power of minus 1. The reason it's minus 1, even though we've multiplied by 2, is because we multiplied by 2. In order to get a balance, we have to now divide by 2. So that becomes minus 1 instead of what it was, which was 0. We've effectively moved the Bicimal point which way? Well, we've effectively moved it to the right, but actually we've doubled the value in order to divide half the value here through the exponent. There are lots of assumptions made, and one is that the sign bit of 1 means it's a negative number, and a sign bit of 0 means it's a positive number. And inside the mantissa we must add 127 in decimal because there's a bias on the exponent. The reason for that is purely technical and really has not much to do with computer science. The exponent is biased with 127, so we have to add 127 to the true exponent. That is, it's 127 minus 1, because the exponent is minus 1. That's 126 in decimal, and in binary it's 11111110 if we read from the most significant bit on the left hand side. The mantissa part is equivalent to 0.5 in decimal, and we know that because it started off as a decimal number, but really it's 1.5 because it's normalized, and 0.5 is the fractional part, and 0.5 in binary is 0.1, where this is a Bicimal point here, and that's really 1 over 2 raised to the power of 1, which is 1 over 2 is a half. When we write those out in this dash notation, we get 1 for the sign bit, 0, 1, 1, 1, 1, 1, 1, 0 for the exponent, because remember we biased it 127, and we have the value after the Bicimal point after normalization, which is of course 0.5. So we have a 1 there. And when we back calculate, we find that this number reads as minus 1 times 1.1 to base 2 times 2 raised to the power of 126 minus 127, and that equals 1.5 times 2 to the power of minus 1, which is equal to minus 0.75. We have another example here, and I've taken this image from Wikipedia. It shows us nicely that the sign bit is in bit 31, and the start of the exponent is in bit 30, and the end is in bit 23. The mantissa starts at 22, bit 22, and ends of course at bit 0. We can work out what this value is that's being stored here, and this is what we do over here, just here. We say that we've got a sign bit of 1, sorry, a sign bit of 0, so it's plus 1 times everything, not minus 1, and we have this number here, which is the exponent and is 124. If we take from that 127, we actually get minus 3. So 2 raised to the power of minus 3 times this number is what value we have. Now we're going to translate this into decimal, in which case we get 1.25, because this is 1.25 here. Yeah, this is a quarter here, and that's a half there, but there's no place value to be had. It's just 1.25. So it's 1.25 in base 10 times 2 raised to the power of 3, and that is 0.15625. So let's go back to the beginning. What was the question that we were trying to discuss? A question about the terms mantissa, exponent and sign bit, and what they mean in terms of the IEEE single precision 32-bit standard. What are the bits doing in the 3 parts? What we found was that there's an implied part that's missing there, which is the times, but that what the sign bit is doing is saying whether the number is positive or negative, whether it's to be multiplied by minus 1 or plus 1. and that the mantissa is the fractional binary part of a normalized scientific notation for the number that one is trying to store, and that there's an implied 1, which, because it's normalized before a Bicimal point, and that the mantissa is after that Bicimal point, because all is in binary and not in decimal. The exponent is what the mantissa, 1 point mantissa, times 2 raised to the power of the exponent is, and that's the value overall. And in our example we had this one here, minus 1.1 binary times 2 to the 0, and let's do an example again. This is very easy. We've got a mantissa of, this is already normalized, of 0.1. So to put this into our binary 32 float standard single precision, we would actually now just say the sign bit is 1 because it's negative, and the exponent is 0, but we've got to add 1 to 7, and so that's 1, 2, 3, 4, 5, 6, 7. So altogether we should have 8 here. Just making sure I've done that. 1, 2, 3, 4, 5, 6, 7, 8. So there's the 8 bits for the exponent, and now we just need to have the mantissa, and we've got that right in front of us. It's actually 0.1, because we said this was a binary number, and so now we've got the other digits to put in, which gives us this number. If you take this number and back calculate, we know it's a negative number because this is a sign bit. We know that these 8 bits here come out to 127, so therefore it must have been 2 raised to the power of 0, and we know that this is 0.1 in binary, which is a half, because there's an implied 1 that's already there due to normalization. We can back calculate this number too, but I'm going to go on to this one, which shows us a decimal representation of 0.15625 as a sign mantissa exponent, or sign exponent mantissa, perhaps we should say, in 32 bits. This number that's representing is going to be plus 1 times something or other because it's a 0 sign bit. This number here in the exponent is going to be 124, that's 124, minus 127, and that gives us in fact minus 3. So that is minus 3 coded there. And in the mantissa part, which we might say is the Bicimal fractional part, we have 0 and 1, which is of course 0 halves but 1 quarter, so this 0.25 here on the right hand side being represented. So we can write that down as this here, this expression is equal to this, 1.25 base 10 times 2 to the minus 3, and that's equal to that. And we can check this out in the calculator, which we'll do just now. So if we take that, either one of these we can do, we do it in decimal, 1.25 times 2 raised to the power of 3, negative that is, so minus 3, and we ask for equals, and we get that number. Similarly, we can do it in binary, but not on this calculator because it doesn't do binary calculations in fractional parts. Right, so I hope this has been helpful to you. in this time we spent, this 25 minutes, to understand how we could explain those three parts. I'll just do it one more time. The term mantissa refers to the binary fractional part of a supposed normalized binary number, and in binary this would be prefixed by 1, and the exponent is the power to the base 2 that the mantissa, with its implicit 1 in front of its Bicimal point, will be raised to by multiplying, and the sign bit dictates whether the whole number is multiplied by -1 or +1, whether it's a negative number or a positive number. And so in brief, this.